Hello again everyone, welcome back to ptet.chemistry channel. This is the start of section B, topical MCQs on classification topic 10.5, which is on halogenoalkane, at least in my classification, right? So with these last 10 questions, well, this type of last 10 questions in a Cambridge International A-Level MCQ component, we talk about option A being relevant to 1, 2, and 3. Statement 1, 2, and 3 relevant to whatever they're asking. If 1 and 2 is what they're asking, then that is option B. Option C is to do with 2 and 3 being relevant to what they're asking, and if only 1 is relevant to whatever they're asking, there's option D. Okay, these kind of questions are getting more and more popular with the other examination body as well. I've seen them in IB chemistry as well as some other of the newer specification of the UK A-levels. Straight into these questions. So this is the energy profile diagram. Halogenoalkane reacts with aqueous alkali. So this is a classic hydrolysis reaction. Hydrolysis of halogenoalkane. You use aqueous because that is in water. That's why it's called hydrolysis. Okay, and the alkali itself, it has hydroxide. So you can also use that as a competing nucleophile. So it's actually a nucleophilic substitution reaction. Okay, and from here you can see the carbon halogen bond gets broken and you kick out a halide, and the OH minus replaces the halide, the halogen or the halide, and that's why it's a competing nucleophile. This is a hydrolysis reaction. This is the type of reaction, but the specific mechanism is called nucleophilic substitution reaction. This is a single hump reaction profile diagram. It goes via this maximum energy, and it's go via one stage only, so we call it single hump or one stage reaction profile diagram. So that top level there is called transition state. It is not an intermediate because it doesn't have a middle trough, it doesn't have a middle low point, it doesn't proceed via a double hump. Okay, so you know this is a SN2 mechanism because it's a single step mechanism. Everything happens in one go. Between X and Y, so what happened there is your carbon halogen bond will get weaker and it will lengthen. Okay, because as this approaches from the back, this bond will get weaker and weaker. At the transition state, what you have essentially, I hope you can see, it should be a primary halogenoalkane for SN2 reaction. So you will have an R group, you will have that, you will have H and H. So the OH is incoming and then the halogen is outgoing. There will be a negative charge because the OH minus bring with it a negative charge to a compound with no charge. This is with a double dagger. It's called transition state. You can watch the full mechanism in the organic chemistry mechanism playlist or under the halogenoalkane playlist on my channel, okay, for the theory behind it. So this bond will get longer and breaks eventually. This bond will get shorter and it will form eventually. So 2 is actually correct. Okay, they're asking for correct statement. As I mentioned, it's an example of nucleophilic substitution. And then the energy difference between X and Z from the lowest point to the highest point, that is indeed activation energy for the reaction. Okay, so all of them are correct, so that's option A. Moving on to the next question is also another hydrolysis. Okay, as you can see, halogenoalkane and OH minus, very popular, yeah, this kind of question, right? But in this hydrolysis, since you are producing NaX and all sodium salts are soluble, so what we do is we monitor the number of moles of NaX formed. Okay, so in a given time, the amount of sodium halide formed was greater with Y than with CH3, CH2Cl. So with that, you need to break CCl. With Y, you need to break a different carbon halogen bond. But the fact that you get more of the sodium halide formed, if you have that point in time, if you could snap freeze that time frame, you have more of the sodium halide formed than that. Okay, so the rate is faster. The rate is faster than breaking the CCl. Okay, so first of all, if you look at option 2, you need to break CBr, and then the next one you need to break CI. Okay, so breaking CBr and breaking CI, both of these, if you look at the bond energy, oops, sorry, I don't want the HI. In a theory paper, you will be expected to state the value from the data booklet. Okay, and you can get this value from the data booklet easily. And you can get the trend very easily as well. So the halogen gets bigger, the bond gets longer, the bonds get weaker. Okay, therefore they are easier to break. So for sure that the carbon bromine and the carbon iodine will break easier, will break faster than breaking the carbon chlorine bond there, and therefore you will get more of the sodium halide being formed faster. Okay, so 2 and 3 are definitely correct. As for option 1, how would you decide? Whether it would give you this graph or not? Okay, because option 1, you have 2 regions. The first region is there, the second region is there. You have 2 times CCl bonds to break. So when you think about the possibilities, okay, so the hydroxide can attack there or there. So there is more reactive CCl sites, greater probability. Okay, so the fact that you get more NaX form over time because the reaction is faster. The reaction is faster because you have more potential reactivity site, whereas here you only have 1 CCl bond to break. The OH minus is just targeting this side. For here, it can go here or it can go here because you have more reactivity site. It can, if it attacks here, it can also give you the sodium halide. If it attacks there, it can also give you the sodium halide. Because of the increased probability, you're always going to get more moles of NaX form per unit time as well, simply because you are hydrolyzing more than just one. You're hydrolyzing more than just one carbon chlorine bond in that reference halogenoalkane there. So 1 is entirely possible to generate this trend as you see here. Okay, so all 3 of them are sensible options. Moving on to the next questions. It's also hydrolysis again, believe it or not. Here you are breaking a CBr bond, and here you have the COH bond. So you call that hydrolysis, but it's actually nucleophilic substitution type of reaction. And here you replace the OH to CCl. This is also nucleophilic substitution. Okay, and for this step you need PCl5, or you need SrCl2, or you need PCl3Cl2. Each of these will involve balance equation, which you will be expected to be able to write in a theory paper. Okay, in a theory paper, if you can't write this equation, if you can't balance it properly, you won't score it. Okay, they can ask this in paper 2 or paper 4 theory papers. Yeah. If we look at option 2, in step X, that's say hot aqueous sodium hydroxide. Well, you need aqueous because you're doing hydrolysis. You need sodium hydroxide as the nucleophile to replace the Br to break the CBr bond. You need hot because you do need to reflux it for hydrolysis. Okay, so 2 is correct. Step X is indeed a nucleophilic substitution. Okay, a hydrolysis reaction of a halogenoalkane is actually a nucleophilic substitution mechanism. Okay, and for step 3, for number 3 in step Y, you don't use sodium chloride as your chlorinating agent. You have to use one of these. So 3 will not give you, sodium chloride will not give you the replacement or the substitution of the OH with Cl. Alright, so 1 and 2 are correct. That's option B. Okay, with this next question, so this looks something different. It's not exactly hydrolysis of a halogenoalkane, but it is not it is hydrolysis, but it is hang on. It's not exactly hydrolysis because it's not hydroxide, but this is what you call an alkoxide. And you learn this in alcohol chemistry, because when you have CH3, CH2OH, you can react it with a reactive metal like sodium or potassium. You can get this thing called alkoxide. Of course, you need to balance every equation you write. So that thing is called sodium alkoxide, and that thing has a lone pair on the oxygen, which can act as a nucleophile. So what you have is, instead of silicon tetrachloride, which you use as part of the chlorides of period 3 chemistry, you learn all that, and the fact that you now have a nucleophile, what happens is that can attack it. But do I make the Cl leave straight away? I could do, but I'm not sure whether it's one step or two step. It does not matter really. So what you have in the end is you have all CH2 CH3, which is C2H5 then, that's CH3 CH3 plus Cl minus. So instead of carbon, they talk about silicon. Silicon is just below carbon, and you should be able to relate periodicity, alright? Cl minus is displaced by the ethoxide. So this is a 2-carbon alkoxide. It's called an ethoxide ion, and indeed it is displaced by it. It's being substituted by the alkoxide. Yeah? Nucleophilic attack by that is called nucleophilic attack because when you, so this is a redox reaction, by the way, yeah, and you know it's a redox because sodium 0 as an element becomes sodium plus 1, hydrogen plus 1 become hydrogen 0. So there is actually a lone pair on the oxygen there, which allows it to act as a nucleophile and attack the silicon. So the oxygen-carbon bond is not broken. Well, the oxygen-carbon bond is somewhere there, okay? So what you have is you have CH3, CH2, O. So that is your carbon-oxygen bond. In fact, that is not broken. All you break is the silicon chlorine, and you are forming oxygen-silicon bond. So 3 is incorrect. Only 1 and 2 are correct. Hang on. I just said that you don't break it, right? Oh my. So I just said that it's not broken. So that is indeed a correct statement. So all 3 are correct. So sometimes when they introduce this idea of not broken, you keep on thinking in your mind that, oh, it's negative, and then sometimes you make the wrong choices. So a lot of MCQ is about reading carefully and not falling into this kind of trick. Yeah, so you might be thinking the right thing, but if you were like me, you will make that mistake, and it will cost you 1 mark. It's 1 or 0, right? So very easy to score, very easy to lose mark as well, right? So indeed, the carbon-oxygen bond is not broken, so that is true. So all 3 are correct. This is the last question of this halogenoalkane topical MCQs for section B type of question. Properties fluoroalkane. So we know they are non-flammable. We use fluoroalkane like Teflon. So this is tetrafluoroethene. So this is Teflon. Oops, sorry. I meant to write the polymeric chain. Okay, it's also called polytetrafluoroethene. You use it in your non-stick cooking pan, and clearly they are non-flammable, okay, because otherwise your cooking pan will light up on fire. They are less reactive than the corresponding chloroalkane. That is true because the energy of a carbon-fluorine bond is stronger than the energy of a carbon-chlorine bond. They don't disintegrate when you cook your food under high temperature as well. Otherwise, you don't really want to be using it in your cooking at all, alright? The bonds are stronger because fluorine is smaller, so carbon-fluorine bond is stronger than the carbon-chlorine bond, which is longer due to the bigger chlorine atom. You can refer this from the data booklet, of course. And as I mentioned, CF bond is stronger than the CCl bond, so indeed they are related to each other. So all 3 options are correct there. This is the end of this tutorial videos, 5-question series. So if you enjoyed these videos, please subscribe to the channel. Share them with your friends, your class group chat, your juniors, your seniors, your students if you are teachers, and anyone else you think might benefit from the videos on my channel. So I'll see you in the next video, and thank you for watching.